Welcome, cosmic explorers, to an extraordinary journey through our home galaxy, the magnificent Milky Way. Prepare to traverse its vastness, delve into its mysteries, and uncover the incredible stories written in its stars, gas, and dust. This isn't just a tour, it's an immersion into the very fabric of our galactic existence, revealing wonders at every turn. 1. Size of the Milky Way. Our cosmic island, the Milky Way, is an astonishingly vast structure, stretching across an immense expanse of space that truly boggles the mind. Imagine a disk so colossal that light, the fastest thing we know, takes approximately 100,000 to 120,000 years to travel from one edge to the other. To put that into perspective, if you could shrink the Milky Way down to the size of North America, our entire solar system would be no larger than a grain of sand. This incredible diameter encompasses billions upon billions of stars, vast clouds of gas and dust, and the enigmatic presence of dark matter, all bound together by gravity. The true scale is difficult to grasp, even for seasoned astronomers, as our own perspective from within makes direct measurement a complex endeavor. Yet, through clever astronomical techniques, including observing the distribution of stars, globular clusters, and the rotation of gas, scientists have pieced together this astounding dimension. This immense size is a fundamental characteristic that dictates everything from the number of stars it can host to its gravitational interactions with neighboring galaxies, setting the stage for the grand narrative of our galactic home. 2. Shape of the Milky Way. Beyond its overwhelming size, the Milky Way possesses a distinct and elegant shape, classified primarily as a barred spiral galaxy. Envision a cosmic pancake, relatively flat and thin, with a prominent central bulge at its heart. Emerging from this luminous core are graceful, sweeping arms that spiral outwards, much like a pinwheel slowly turning in the cosmic breeze. However, it's not a perfect symmetrical spiral. Observations suggest a more intricate and somewhat lopsided structure, influenced by internal dynamics and external gravitational nudges. The barred aspect refers to a dense, elongated bar of stars that cuts straight through the galactic center, from which the main spiral arms emerge. This bar is a significant feature, influencing the flow of gas and the formation of stars within the inner galaxy. From a bird's-eye view, if we could somehow observe it from above, we would see this majestic, swirling pattern, a cosmic dance of stars and gas that has captivated astronomers for centuries. This characteristic shape is not merely aesthetic. It's a dynamic consequence of gravity, rotation, and the ongoing processes of star formation and galactic evolution. 3. Thickness versus diameter comparison. While the Milky Way's diameter spans a breathtaking 100,000 to 120,000 light-years, its thickness is remarkably modest in comparison, giving it that characteristic pancake or disk appearance. The main stellar disk, where most of the stars and gas reside, is only about 1,000 to 2,000 light-years thick. This means that if you were to represent the Milky Way as a DVD, its diameter would be about 100 times greater than its thickness. This extreme flatness is a direct result of its formation and rotation. As the primordial gas cloud that would become our galaxy collapsed under gravity, its rotation caused it to flatten into a disk, much like a spinning ball of dough flattens into a pizza crust. While the thin disk contains the majority of young, bright stars and active star-forming regions, there's also a thicker, more diffuse disk component, containing older stars, which extends a bit further vertically. This stark contrast between the vast diameter and relatively slender thickness is a key feature that defines spiral galaxies, influencing everything from the paths of stars to the distribution of interstellar matter. 4. Number of stars. Within the immense confines of the Milky Way, an astronomical number of stars glitter, forming a truly breathtaking celestial tapestry. While an exact count remains elusive due to the sheer scale and our limited perspective from within, Current estimates place the total number of stars between 100 billion and 400 billion. To put that into context, imagine counting one star every second. It would take you over 3,000 years to reach 100 billion. This colossal stellar population includes a dazzling array of types, from tiny, dim red dwarfs, which are the most common, to colossal, luminous blue giants, and everything in between. Each of these stars is a sun in its own, many of them potentially hosting their own planetary systems. This vast stellar census is derived from various observational techniques, including estimating the galaxy's total mass and then calculating how much of that mass is likely locked up in stars, factoring in different stellar populations and their typical masses. The sheer density of stars, particularly towards the galactic center, creates the luminous band we observe in our night sky, a testament to the unimaginable richness of our galactic home.
5. Location of the Sun. Our own star, the Sun, along with its planetary entourage, including Earth, holds a rather modest but strategically important position within the vast expanse of the Milky Way. We are not at the center, nor are we languishing at the extreme edges. Instead, the Sun is situated in one of the galaxy's minor spiral arms, specifically the Orion arm, sometimes referred to as the Orion spur. This arm is nestled between two of the major spiral arms, the Perseus arm and the Sagittarius arm. Our solar system resides approximately 2/3 of the way out from the galactic center, roughly 26,000 to 27,000 light-years away from the supermassive black hole that anchors our galaxy. This location offers a relatively clear view of both the inner and outer regions of the Milky Way, making it an excellent vantage point for astronomical observations. It also means we're not subjected to the intense radiation and gravitational forces found closer to the galactic core, providing a relatively stable and less crowded environment for life to thrive. This suburban address in the cosmic neighborhood plays a crucial role in our understanding and exploration of the galaxy itself. 6. Galactic center characteristics. The galactic center is arguably the most dynamic, mysterious, and awe-inspiring region of the Milky Way, a bustling metropolis of stars, gas, and intense gravitational forces. It's not a calm, empty void, but a densely packed environment where stars are crammed together far more tightly than in our solar neighborhood, sometimes only light weeks apart. This extreme stellar density leads to frequent interactions and a high rate of supernovae. The very heart of this region, within a few hundred light-years, is known as the central molecular zone, characterized by vast, dense clouds of molecular gas that are fertile grounds for star formation, despite the harsh conditions. Intense radio emissions, X-rays, and gamma rays emanate from this core, indicating highly energetic processes at play. Dust lanes obscure much of the visible light from this region, making it a challenge to study directly, but observations in infrared and radio wavelengths reveal its incredible complexity. Understanding the galactic center is key to comprehending the evolution and dynamics of the entire galaxy, as it acts as the gravitational anchor for billions of stars. 7. Sagittarius A star black hole. At the absolute heart of our galactic center, hidden behind veils of gas and dust, lies the supermassive black hole known as Sagittarius A star, pronounced Sagittarius A star. This colossal cosmic behemoth is the gravitational anchor for the entire Milky Way. While invisible itself, its presence is unequivocally confirmed by observing the incredibly rapid and tightly bound orbits of stars swirling around an unseen mass. These stellar dances reveal that Sagittarius A star possesses a mass equivalent to approximately 4.3 million times that of our Sun, all packed into a region smaller than the orbit of Mercury. Despite its immense mass, it's not actively consuming stars at a high rate. It's currently in a relatively quiescent state, occasionally flaring up as gas or dust clouds get too close and are pulled into its accretion disk. Studying Sagittarius A star provides invaluable insights into the behavior of supermassive black holes, their role in galaxy evolution, and the extreme physics of gravity. It's a cosmic engine, silently dictating the grand ballet of billions of stars across the vastness of our galaxy. 8. Spiral Arms Overview. The most iconic feature of a spiral galaxy, like the Milky Way, is its majestic spiral arms, sweeping structures that define its characteristic pinwheel shape. These arms are not rigid, permanent structures of stars, but rather regions where stars, gas, and dust are temporarily compressed, leading to enhanced star formation. Think of them more like traffic jams on a cosmic highway, where vehicles, stars, and gas slow down, causing a pileup. As stars and gas pass through these density waves, the increased density triggers the collapse of molecular clouds, igniting new generations of stars. This is why the spiral arms appear brighter and bluer. They are teeming with young, hot, massive stars, which are much more luminous than older, cooler stars. These arms are not static. They are dynamic features, constantly forming and dissolving as the galaxy rotates. They play a crucial role in the galaxy's evolution, acting as cosmic nurseries that continuously replenish the stellar population and distribute heavy elements throughout the galactic disk. 9. Major spiral arms. The Milky Way is believed to possess at least 2 prominent major spiral arms, along with several minor ones. The 2 most significant and well-defined major arms are the Perseus arm and the Scutum-Centaurus arm. The Perseus arm is located further out from the galactic center than our solar system, and is one of the most massive and distinct features of our galaxy. It's rich in young, luminous stars, star-forming regions, and giant molecular clouds, making it a region of intense stellar activity. The Scutum-Centaurus arm, on the other hand, lies closer to the galactic center, inside our solar system's orbit, and is also a major player in the galaxy's structure. Both of these arms extend for tens of thousands of light-years, wrapping around the galactic core. Their existence and structure are inferred through observations of various tracers, such as hydrogen gas clouds, young star clusters, and nebulae, which tend to congregate along these density enhancements. These major arms are the backbone of the Milky Way's spiral pattern, guiding the flow of gas and the rhythm of star birth across vast cosmic distances.
15. Halo of the Milky Way. Beyond the relatively flat, star-rich disk of the Milky Way lies a vast spherical region known as the galactic halo. This expansive, diffuse envelope extends far beyond the visible boundaries of the disk, reaching hundreds of thousands of light-years into intergalactic space. Unlike the disk, which is teeming with young, bright stars and gas, the stellar halo is sparsely populated, primarily containing very old, metal-poor stars, often found in globular clusters. These clusters are ancient relics, some of the first structures to form in the early universe, and their orbits are highly eccentric, plunging through the disk and soaring far above it. The halo also contains very little gas or dust, making star formation rare. However, the most significant component of the halo, though invisible, is the enigmatic dark matter. This vast dark matter halo is thought to be the dominant gravitational influence, extending much further than the stellar components and providing the gravitational scaffolding that holds the entire galaxy together. 16. Stellar halo versus dark matter halo. When we speak of the Milky Way's halo, it's crucial to distinguish between its 2 primary components, the stellar halo and the dark matter halo, as they represent very different aspects of our galaxy structure. The stellar halo consists of a sparse distribution of very old, typically metal-poor stars and globular clusters that orbit the galactic center in highly eccentric paths, forming a roughly spherical distribution extending far beyond the disk. These stars are thought to be remnants of smaller galaxies that the Milky Way has cannibalized over billions of years.
In contrast, the dark matter halo is an invisible, much more massive, and far more extensive spherical distribution of dark matter particles that completely envelops the entire visible galaxy, including the stellar halo and the disk. It is the dominant gravitational component of the Milky Way, far outweighing the visible matter. While the stellar halo provides clues about the galaxy's merger history, the dark matter halo is the fundamental gravitational backbone, explaining the galaxy's rotation curve and overall stability. 17. Dark matter role in galaxy structure. Dark matter plays an absolutely indispensable and dominant role in shaping the structure and dynamics of the Milky Way, and indeed all large galaxies. Despite being invisible and undetectable by conventional means, its gravitational influence is profound and pervasive. Without dark matter, our galaxy simply wouldn't hold together as it does. Observations of the Milky Way's rotation curve reveal that stars and gas in the outer regions orbit the galactic center much faster than they should if only visible matter were present. This discrepancy is the strongest evidence for dark matter. It acts as an invisible gravitational glue, providing the extra mass needed to explain these high orbital velocities and prevent the outer parts of the galaxy from flying apart. The dark matter halo provides the gravitational well within which the visible matter of the disk and bulge resides, effectively acting as the skeletal framework upon which the luminous galaxy is built. Its presence dictates the scale, stability, and evolution of the Milky Way. 19. Mass estimates. Estimating the total mass of the Milky Way is a complex astronomical challenge, given our internal perspective and the presence of invisible dark matter. But scientists have developed sophisticated methods to arrive at robust figures. Current estimates place the total mass of our galaxy at approximately 1.5 trillion, 1.5 times 10 to the 12 times the mass of our Sun. However, it's critical to understand the breakdown. Only about 10 to 15% of this colossal mass is attributed to visible matter, stars, gas, and dust. The overwhelming majority, roughly 85 to 90%, is accounted for by the enigmatic dark matter. These estimates are derived by observing the orbital velocities of stars and gas clouds at various distances from the galactic center, especially in the outer halo, and applying Newton's laws of gravity. The faster objects orbit, the more mass must be enclosed within their orbits. By mapping these velocities, astronomers can infer the distribution of mass, revealing the pervasive influence of the invisible dark matter halo that dominates the galaxy's overall gravitational budget. 19. Composition of the galaxy. The Milky Way is a grand cosmic ecosystem composed of a diverse array of constituents, though not all equally visible or massive. The most familiar components are stars, which constitute the luminous bulk of the galaxy, ranging from tiny red dwarfs to massive blue giants, along with their stellar remnants like white dwarfs, neutron stars, and black holes. Interspersed between these stars is the interstellar medium, ISM, a vast expanse of gas and dust. This ISM is primarily hydrogen and helium, the raw materials for new stars, and it exists in various phases, from cold, dense molecular clouds to hot, diffuse ionized gas. However, the true dominant component by mass is the elusive dark matter, which doesn't interact with light and is only detectable through its gravitational effects. While invisible, it accounts for roughly 85 to 90% of the galaxy's total mass. Lesser components include cosmic rays, magnetic fields, and the occasional rogue planet. This intricate mix of visible, gaseous, and invisible matter orchestrates the galaxy's evolution, star formation, and overall dynamics. 15. Halo of the Milky Way. Beyond the relatively flat, star-rich disk of the Milky Way lies a vast spherical region known as the galactic halo. This expansive, diffuse envelope extends far beyond the visible boundaries of the disk, reaching hundreds of thousands of light-years into intergalactic space. Unlike the disk, which is teeming with young, bright stars and gas, the stellar halo is sparsely populated, primarily containing very old, metal-poor stars, often found in globular clusters. These clusters are ancient relics, some of the first structures to form in the early universe, and their orbits are highly eccentric, plunging through the disk and soaring far above it. The halo also contains very little gas or dust, making star formation rare. However, the most significant component of the halo, though invisible, is the enigmatic dark matter. This vast dark matter halo is thought to be the dominant gravitational influence, extending much further than the stellar components and providing the gravitational scaffolding that holds the entire galaxy together. 16. Stellar halo versus dark matter halo. When we speak of the Milky Way's halo, it's crucial to distinguish between its two primary components, the stellar halo and the dark matter halo, as they represent very different aspects of our galaxy structure. The stellar halo consists of a sparse distribution of very old, typically metal-poor stars and globular clusters that orbit the galactic center in highly eccentric paths, forming a roughly spherical distribution extending far beyond the disk. These stars are thought to be remnants of smaller galaxies that the Milky Way has cannibalized over billions of years. In contrast, the dark matter halo is an invisible, much more massive, and far more extensive spherical distribution of dark matter particles that completely envelops the entire visible galaxy, including the stellar halo and the disk. It is the dominant gravitational component of the Milky Way, far outweighing the visible matter. While the stellar halo provides clues about the galaxy's merger history, the dark matter halo is the fundamental gravitational backbone, explaining the galaxy's rotation curve and overall stability. 17. Dark matter role in galaxy structure. Dark matter plays an absolutely indispensable and dominant role in shaping the structure and dynamics of the Milky Way, and indeed all large galaxies. Despite being invisible and undetectable by conventional means, its gravitational influence is profound and pervasive. Without dark matter, our galaxy simply wouldn't hold together as it does. Observations of the Milky Way's rotation curve reveal that stars and gas in the outer regions orbit the galactic center much faster than they should if only visible matter were present. This discrepancy is the strongest evidence for dark matter. It acts as an invisible gravitational glue, providing the extra mass needed to explain these high orbital velocities and prevent the outer parts of the galaxy from flying apart. The dark matter halo provides the gravitational well within which the visible matter of the disk and bulge resides, effectively acting as the skeletal framework upon which the luminous galaxy is built. Its presence dictates the scale, stability, and evolution of the Milky Way. 19. Mass estimates. Estimating the total mass of the Milky Way is a complex astronomical challenge, given our internal perspective and the presence of invisible dark matter. But scientists have developed sophisticated methods to arrive at robust figures. Current estimates place the total mass of our galaxy at approximately 1.5 trillion, 1.5 times 10 to the 12 times the mass of our Sun. However, it's critical to understand the breakdown. Only about 10 to 15% of this colossal mass is attributed to visible matter, stars, gas, and dust. The overwhelming majority, roughly 85 to 90%, is accounted for by the enigmatic dark matter. These estimates are derived by observing the orbital velocities of stars and gas clouds at various distances from the galactic center, especially in the outer halo, and applying Newton's laws of gravity. The faster objects orbit, the more mass must be enclosed within their orbits. By mapping these velocities, astronomers can infer the distribution of mass, revealing the pervasive influence of the invisible dark matter halo that dominates the galaxy's overall gravitational budget. 19. Composition of the galaxy. The Milky Way is a grand cosmic ecosystem composed of a diverse array of constituents, though not all equally visible or massive.
The most familiar components are stars, which constitute the luminous bulk of the galaxy, ranging from tiny red dwarfs to massive blue giants, along with their stellar remnants like white dwarfs, neutron stars, and black holes. Interspersed between these stars is the interstellar medium, ISM, a vast expanse of gas and dust. This ISM is primarily hydrogen and helium, the raw materials for new stars, and it exists in various phases, from cold, dense molecular clouds to hot, diffuse ionized gas. However, the true dominant component by mass is the elusive dark matter, which doesn't interact with light and is only detectable through its gravitational effects. While invisible, it accounts for roughly 85 to 90% of the galaxy's total mass. Lesser components include cosmic rays, magnetic fields, and the occasional rogue planet. This intricate mix of visible, gaseous, and invisible matter orchestrates the galaxy's evolution, star formation, and overall dynamics.
20. Interstellar medium. The interstellar medium, or ISM, is the incredibly vast and diffuse material that fills the space between stars within the Milky Way. Far from being an empty vacuum, the ISM is a dynamic and complex environment, a cosmic soup of gas and dust that serves as the raw material for new stars and planets. It's predominantly composed of hydrogen, about 70%, and helium, about 28%, with trace amounts of heavier elements, often referred to as metals by astronomers. The ISM exists in multiple phases, each with different temperatures and densities, from very cold, dense molecular clouds where stars are born, to warm, neutral hydrogen clouds, to hot, ionized gas created by supernova explosions. Interspersed within this gas are tiny solid particles of interstellar dust, composed of silicates, carbon, and ice, which absorb and scatter starlight, leading to dark nebulae and reddening effects. The ISM is in a constant state of flux, being enriched by stellar winds and supernova remnants, and depleted by star formation, making it a crucial component in the galaxy's ongoing cycle of birth, life, and death. 21. Molecular clouds. Molecular clouds are among the most fascinating and critical components of the interstellar medium, acting as the primary nurseries for star formation within the Milky Way. These are vast, cold, and relatively dense regions of interstellar gas and dust where conditions are just right for atoms to combine into molecules, predominantly molecular hydrogen, H2, which is notoriously difficult to detect directly. However, other molecules like carbon monoxide, CO, are excellent tracers. Molecular clouds are incredibly cold, often just a few tens of Kelvin above absolute zero, allowing gravity to overcome the internal pressure of the gas. They are also dense enough to shield their interiors from harsh ultraviolet radiation, enabling molecules to survive. These clouds can vary significantly in size, from small, dark nebulae that might form a few stars to giant molecular clouds that span hundreds of light years and contain enough material to form thousands of stars. Their collapse marks the beginning of the stellar birth process, making them fundamental to the galaxy's ongoing evolution. 22. Giant molecular clouds. Giant molecular clouds, GMCs, are the behemoths of the interstellar medium, representing the largest and most massive structures within the Milky Way where star formation occurs on a grand scale. These colossal clouds of molecular gas and dust can span hundreds of light years across and contain hundreds of thousands, sometimes even millions, of solar masses of material. They are incredibly cold, often just 10-20 Kelvin, and dense enough for gravity to dominate, leading to their eventual collapse and fragmentation. Within a single GMC, thousands of new stars can be born simultaneously or in rapid succession, forming entire star clusters. They are often found concentrated along the galaxy's spiral arms, where the compression of gas enhances their formation.
The dynamic processes within GMCs, including turbulence, magnetic fields, and the feedback from newly formed massive stars through stellar winds and supernovae, dictate the efficiency and patterns of star formation, making them central to understanding the ongoing stellar population growth of our galaxy. 23. Star-forming regions. Star-forming regions are the vibrant, energetic nurseries scattered throughout the Milky Way where new stars are actively being born from collapsing clouds of gas and dust. These regions are typically found within or at the edges of giant molecular clouds, particularly concentrated along the galaxy's spiral arms. They are characterized by several telltale signs: the presence of young, hot, luminous blue stars, which are short-lived and therefore indicate recent formation; emission nebulae, HII regions, glowing brightly as the intense ultraviolet radiation from these young stars ionize surrounding hydrogen gas; and dark nebulae, which are dense pockets of dust obscuring background starlight, often the very clouds from which stars are emerging. Famous examples include the Orion Nebula and the Eagle Nebula, both spectacular displays of stellar genesis. These regions are crucial for replenishing the galaxy's stellar population, enriching the interstellar medium with heavier elements through stellar nucleosynthesis, and driving galactic evolution through the powerful feedback from massive young stars. 24. Nebulae in the Milky Way. Nebulae are among the most visually stunning and scientifically significant objects within the Milky Way, representing vast, diffuse clouds of gas and dust scattered throughout interstellar space. The word nebula itself means cloud in Latin, and these cosmic clouds come in various forms, each telling a different story of stellar life and death. Emission nebulae, like the famous Orion Nebula, glow brightly as they are ionized by the intense ultraviolet radiation from nearby hot young stars. Reflection nebulae, such as those around the Pleiades, shine by scattering the light from nearby stars. Dark nebulae, like the Horsehead Nebula, are so dense with dust that they block out the light from background stars, appearing as silhouettes against brighter regions. These are often sites of active star formation. Planetary nebulae are the beautiful, expanding shells of gas ejected by dying low-mass stars. Supernova remnants are the chaotic, expanding debris fields left behind after a massive star explode. Together, these nebulae illustrate the dynamic interplay between stars and the interstellar medium, showcasing the galaxy's continuous cycle of creation and destruction.
25. Planetary nebulae. Planetary nebulae are some of the most beautiful and poignant objects in the Milky Way, representing the final, relatively brief and spectacular evolutionary stage for low to intermediate mass stars, including our own Sun, before they become white dwarfs. Despite their name, they have nothing to do with planets. The term originated in the 18th century because early telescopes made them appear as diffuse, planet-like disks. A planetary nebula forms when a star, having exhausted the hydrogen fuel in its core, expands into a red giant, then sheds its outer layers of gas into space. The remaining hot, exposed core, which will eventually become a white dwarf, emits intense ultraviolet radiation that ionizes the expanding shell of gas, causing it to glow brightly in various colors depending on its chemical composition. These nebulae are relatively short-lived, lasting only tens of thousands of years before the gas disperses into the interstellar medium. They play a crucial role in enriching the galaxy with heavier elements synthesized within the star, contributing to the chemical evolution of the Milky Way. 26. Supernova remnants. Supernova remnants, SNRs, are the spectacular and often chaotic aftermath of a supernova explosion, one of the most energetic events in the universe. These expanding shells of gas and dust are left behind after either a massive star reaches the end of its life and collapses, or a white dwarf in a binary system accretes too much material and undergoes a thermonuclear runaway.
The shock wave from the explosion sweeps up and compresses the surrounding interstellar medium, heating it to millions of degrees and causing it to glow fiercely across the electromagnetic spectrum, particularly in X-rays and radio waves. SNRs are crucial for the chemical evolution of the Milky Way, as they violently eject newly synthesized heavy elements like oxygen, iron, and silicon into interstellar space, enriching the galaxy from which future generations of stars and planets will form. They also play a significant role in stirring up the interstellar medium, triggering new star formation by compressing gas clouds and accelerating cosmic rays, making them powerful engines of galactic evolution. 27. Star birth processes. The birth of a star within the Milky Way is a majestic and complex process, beginning deep within dense, cold molecular clouds. It all starts when a region within such a cloud becomes gravitationally unstable, perhaps triggered by a passing shock wave from a supernova or a galactic spiral arm. This instability causes a small clump of gas and dust to begin collapsing under its own gravity. As the clump contracts, it heats up and spins faster, eventually forming a protostar surrounded by a swirling disk of material. This accretion disk feeds material onto the growing protostar, which continues to gain mass and shrink. Over millions of years, the core of the protostar becomes incredibly hot and dense. When the temperature and pressure in the core reach a critical point, around 10 million Kelvin, nuclear fusion ignites, converting hydrogen into helium and releasing enormous amounts of energy. At this moment, the protostar officially becomes a main sequence star, like our Sun, shining brightly and beginning its long, stable life. 28. Star death processes. The death of a star in the Milky Way is as varied and dramatic as its birth, with its ultimate fate largely determined by its initial mass. Low to intermediate mass stars, like our Sun, end their lives relatively peacefully. After exhausting the hydrogen in their core, they swell into red giants, shed their outer layers to form a beautiful planetary nebula, and leave behind a dense, hot, Earth-sized core known as a white dwarf, which slowly cools over billions of years. More massive stars, however, meet a far more spectacular end. After exhausting their nuclear fuel, their cores collapse catastrophically under immense gravity, triggering a powerful supernova explosion. What remains after a supernova depends on the progenitor star's initial mass. For stars roughly 8 to 25 times the Sun's mass, the core collapses into an incredibly dense neutron star. For the most massive stars, over 25 solar masses, the collapse is so complete that it forms a stellar mass black hole, an object so dense that nothing, not even light, can escape its gravitational pull. These stellar deaths enrich the galaxy with heavy elements and shape its evolution. 29. White dwarfs in the galaxy. White dwarfs are the incredibly dense, compact remnants of low to intermediate mass stars, like our Sun, after they have exhausted their nuclear fuel and shed their outer layers. These stellar corpses are about the size of Earth, yet they contain roughly the mass of the Sun, meaning a teaspoon of white dwarf material would weigh several tons. They no longer undergo nuclear fusion and simply cool down over billions of years, slowly fading into cosmic oblivion as black dwarfs, though none are thought to exist yet, as the universe isn't old enough. The Milky Way is teeming with white dwarfs, representing the final evolutionary stage for over 90% of all stars. Their presence provides a cosmic clock, as their cooling rates can be used to estimate the age of stellar populations. In binary systems, white dwarfs can sometimes accrete matter from a companion star, leading to spectacular events like novae or even type A supernovae, which are crucial for measuring cosmic distances. 30. Neutron stars in the galaxy. Neutron stars are among the most extreme and exotic objects in the Milky Way, born from the catastrophic core collapse of massive stars, typically 8 to 25 times the Sun's mass, during a supernova explosion.
These incredibly dense stellar remnants are only about 20 kilometers, 12 miles in diameter, yet they pack more mass than our entire sun into that tiny sphere. Their density is mind-boggling. A single teaspoon of neutron star material would weigh billions of tons. They are composed almost entirely of neutrons, hence their name, tightly packed together. Many neutron stars are observed as pulsars, rapidly spinning objects that emit beams of radio waves or other radiation from their magnetic poles, which sweep across Earth like a lighthouse beacon. The Milky Way likely contains hundreds of millions of neutron stars, though only a fraction have been detected due to their small size and specific emission patterns. They are laboratories for extreme physics, allowing scientists to study matter under conditions impossible to replicate on Earth. 31. Black holes population. The Milky Way is home to a diverse and significant population of black holes, ranging from the supermassive behemoth at its center to numerous stellar mass black holes scattered throughout the galaxy. The most prominent is Sagittarius A star, the supermassive black hole with a mass of about 4.3 million suns, which anchors the entire galaxy. Beyond this central giant, stellar mass black holes are born from the gravitational collapse of the most massive stars, typically exceeding 25 solar masses, at the end of their lives, following a supernova explosion. These individual black holes typically have masses ranging from a few to tens of solar masses. While difficult to detect directly, their presence is inferred when they are part of a binary system, accreting material from a companion star, which then emits X-rays. Estimates suggest there could be tens of millions to hundreds of millions of stellar mass black holes lurking within the Milky Way, though only a few dozen have been definitively identified. Their collective gravitational influence, though individually small, contributes to the overall mass distribution of the galaxy. 32. Hypervelocity stars. Hypervelocity stars are a rare and captivating phenomenon in the Milky Way, representing celestial escapees flung out of the galaxy at incredible speeds. These stars are traveling so fast, hundreds of kilometers per second, sometimes exceeding 1,000 kilometers per second, that they are moving at or above the escape velocity of the Milky Way, meaning they are destined to leave our galaxy entirely and journey into intergalactic space. The leading theory for their origin involves a close encounter with the supermassive black hole Sagittarius A star at the galactic center. If a binary star system passes too close, the black hole's immense gravity can rip the pair apart, capturing one star into a tight orbit while flinging the other away with tremendous force. Another possible mechanism involves supernova explosions in binary systems. Observing and studying hypervelocity stars provides unique insights into the dynamics of the galactic center, the behavior of supermassive black holes, and the gravitational potential of the Milky Way's halo, offering a glimpse into objects destined to become intergalactic wanderers. 34. Rogue planets. Rogue planets, also known as free-floating planets or unbound planets, are celestial bodies with planetary masses that roam interstellar space, unattached to any star system. These solitary wanderers are thought to be quite common throughout the Milky Way, potentially outnumbering stars. Their origins are still a subject of active research, but leading theories suggest they are formed in two primary ways. Either they are ejected from their nascent stellar systems during the chaotic early stages of planet formation due to gravitational interactions with other planets or the central star, or they might form directly from the collapse of small molecular clouds, similar to how stars form, but without accumulating enough mass to ignite nuclear fusion. Detecting rogue planets is extremely challenging, as they emit no light of their own and are only observable through gravitational microlensing events, where their gravity temporarily magnifies the light from a background star. Their existence challenges our traditional view of planets as strictly bound to stars and adds another layer of complexity to the cosmic landscape of our galaxy. 35. Exoplanets in the Milky Way. The Milky Way is teeming with exoplanets, worlds orbiting stars other than our Sun, and their discovery has revolutionized our understanding of planetary systems and the potential for life beyond Earth. Thanks to missions like Kepler and TESS and ground-based observatories, thousands of exoplanets have been confirmed, and statistical analyses suggest that virtually every star in our galaxy likely hosts at least one planet. This means there could be hundreds of billions of exoplanets within the Milky Way. These discovered worlds exhibit an astonishing diversity in size, mass, and orbital characteristics, ranging from super-Earths and many Neptunes to gas giants larger than Jupiter, some orbiting incredibly close to their host stars and others in vast, distant orbits. The sheer abundance of exoplanets indicates that planet formation is a common byproduct of star formation, making the Milky Way a galactic archipelago of countless worlds, each with its own unique story and potential for discovery.
35. Habitable zone frequency. The concept of the habitable zone, often called the Goldilocks zone, refers to the range of orbital distances around a star where conditions are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The frequency of planets within the habitable zone in the Milky Way is a central question in astrobiology. While the exact number remains uncertain, recent exoplanet surveys have provided encouraging estimates. Studies suggest that a significant fraction of Sun-like stars, and even more so for smaller, cooler red dwarf stars, host planets within their respective habitable zones. Some estimates indicate that there could be tens of billions of potentially habitable, Earth-sized planets in the Milky Way alone. However, being in the habitable zone is not the sole criterion for habitability. Factors like atmospheric composition, geological activity, the presence of a protective magnetic field, and the stability of the star itself also play crucial roles. Nevertheless, the sheer number of candidates fuels optimism in the search for extraterrestrial life within our galaxy. 36. Distribution of heavy elements. The distribution of heavy elements, or metals in astronomical parlance, meaning all elements heavier than hydrogen and helium, is not uniform across the Milky Way and serves as a powerful tracer of the galaxy's chemical evolution and star formation history. These heavy elements are forged in the cores of stars through nuclear fusion and then dispersed into the interstellar medium, primarily through supernova explosions and stellar winds from massive stars and planetary nebulae from lower-mass stars. Consequently, regions of the galaxy that have undergone more cycles of star formation and stellar death tend to be richer in heavy elements. The galactic center and inner disk generally have higher metallicities than the outer disk and especially the ancient stellar halo, which contains the galaxy's oldest, most metal-poor stars. This gradient in metallicity provides a chronological map, indicating that star formation began in the inner regions and slowly propagated outwards, enriching the galaxy with the building blocks necessary for rocky planets and life over billions of years. 37. Population I and Population II stars. Stars in the Milky Way are broadly categorized into two main populations based on their age, location, and crucially, their metallicity, abundance of elements heavier than hydrogen and helium. Population I stars are typically younger, metal-rich stars found predominantly in the thin disk and spiral arms of the galaxy. They include bright, blue, massive stars, as well as stars like our Sun. Their high metallicity indicates they formed from interstellar gas that had already been enriched by previous generations of stars. In contrast, Population II stars are generally older, metal-poor stars. They are found in the thick disk, the galactic bulge, and most prominently in the spherical stellar halo and globular clusters. These stars formed early in the galaxy's history from pristine gas that had not yet been significantly enriched by heavy elements. A theoretical Population III, the very first stars, would have been metal-free, but none have yet been directly observed. This classification provides a fundamental framework for understanding stellar evolution and the chemical history of the Milky Way. 38. Globular clusters. Globular clusters are magnificent, ancient stellar cities within the Milky Way, representing some of the oldest and most densely packed collections of stars in our galaxy. Each globular cluster is a tightly bound, spherical collection of hundreds of thousands to millions of stars, all gravitationally bound and orbiting the galactic center as a single unit. They are found predominantly in the Milky Way's halo, forming a vast spherical distribution that extends far beyond the galactic disk. The stars within globular clusters are almost exclusively very old, typically population 2 stars, characterized by their low metallicity. Their ages, often exceeding 10 billion years, make them invaluable cosmic fossils, providing crucial insights into the early formation and evolution of the Milky Way. There are currently about 150 known globular clusters associated with our galaxy, but their study continues to reveal secrets about the initial conditions of the universe and the early assembly of galactic structures. 39. Open clusters. In contrast to the ancient, densely packed globular clusters, open clusters are younger, more loosely bound aggregations of stars, found predominantly within the disk of the Milky Way, particularly along its spiral arms. These clusters typically contain a few tens to a few thousands of stars, all born from the same giant molecular cloud at roughly the same time. Because they are gravitationally less tightly bound than globular clusters, open clusters tend to disperse over hundreds of millions of years as they interact with other stars and gas clouds in the galactic disk. Their stars are generally younger, brighter, and more metal-rich, population I, than those in globular clusters. Famous examples include the Pleiades and the Hyades. Studying open clusters provides astronomers with a natural laboratory to observe stellar evolution, as all the stars within a cluster have the same age and distance, allowing for precise comparisons of their properties. They are crucial indicators of ongoing star formation within the galactic disk and help trace the spiral arm structure.
40. The local bubble. The local bubble is a vast, irregularly shaped cavity in the interstellar medium, approximately 300 light-years across, within which our solar system and several nearby stars reside. This enormous void is characterized by extremely hot, around 1,000,000 degrees Kelvin, and very tenuous gas, with a density much lower than the average interstellar medium. It is thought to have been created by a series of supernova explosions that occurred over the last 10 to 20 million years, which swept away and heated the surrounding gas, carving out this enormous bubble. The Sun is currently located near the edge of this bubble. The local bubble plays a significant role in defining our immediate galactic neighborhood, influencing the local interstellar environment and the properties of the gas and dust that our solar system interacts with. Its existence highlights the dynamic and often violent nature of the interstellar medium, shaped by the powerful feedback mechanisms of massive stars. 41. The local interstellar cloud. Within the local bubble, our solar system is not entirely in a vacuum, but is currently passing through a slightly denser region of interstellar gas, known as the local interstellar cloud. This cloud is a small, wispy structure, only about 30 light-years across, with a temperature of around 6,000–7,000 Kelvin and a density roughly 10 times greater than the gas in the surrounding local bubble, though still incredibly diffuse by terrestrial standards. The LIC is thought to be a remnant of a larger, cooler cloud that was partially evaporated and pushed around by the supernova explosions that created the local bubble. Our Sun is moving through this cloud at a speed of about 26 kilometers per second, and the interaction between the Sun's heliosphere, the bubble of charged particles created by the solar wind, and the LIC's plasma creates a bow shock, similar to a boat moving through water. Studying the LIC provides direct insights into the composition and properties of the interstellar medium immediately surrounding our solar system, offering a glimpse of the very local galactic environment. 42. Local group of galaxies. The Milky Way is not an isolated island in the cosmos. It is a prominent member of a gravitationally bound collection of galaxies known as the local group. This cosmic neighborhood is a relatively small cluster, spanning about 10 million light-years across, and dominated by two massive spiral galaxies, our own Milky Way and the Andromeda Galaxy, M31. These two giants are currently approaching each other and are on a collision course.
Alongside these two, the local group includes the Triangulum Galaxy, M33, another spiral, and over 50 smaller dwarf galaxies, many of which are satellites of the Milky Way or Andromeda. These smaller galaxies, such as the Magellanic Clouds, are often irregular or elliptical in shape. The local group provides a natural laboratory for studying galaxy interactions, evolution, and the distribution of dark matter on a cluster scale, offering invaluable insights into the broader cosmic web of galaxies that populate the universe. 44. Andromeda-Milky Way Future Collision. One of the most dramatic and inevitable cosmic events awaiting the Milky Way is its future collision with our largest galactic neighbor, the Andromeda Galaxy, M31. These two colossal spiral galaxies are currently hurtling towards each other at a speed of about 110 kilometers per second, driven by their mutual gravitational attraction. While the collision sounds cataclysmic, it won't be a head-on smash-up in the traditional sense, as the distances between stars are so vast. Instead, over several billion years, the galaxies will pass through each other multiple times, their gravitational fields distorting and reshaping both structures. Stars themselves are unlikely to collide, but their orbits will be drastically altered, and immense clouds of gas and dust will be compressed, triggering intense bursts of star formation. Eventually, in about 4.5 billion years, the two spirals are predicted to merge completely, forming a larger, more elliptical galaxy that astronomers have playfully dubbed Milkomeda. This grand merger is a natural part of galaxy evolution, illustrating the dynamic and often violent processes that build larger cosmic structures. 44. Sagittarius Dwarf Galaxy, being absorbed. The Milky Way is currently engaged in a process of galactic cannibalism, slowly but surely absorbing smaller satellite galaxies that venture too close. A prime example of this ongoing merger is the Sagittarius Dwarf Spherical Galaxy, a relatively small galaxy that is currently being torn apart and consumed by our own. Discovered in 1994, this dwarf galaxy is in the process of spiraling into the Milky Way, its stars and gas being stripped away by our galaxy's immense tidal forces. As it orbits, it leaves behind long, coherent streams of stars and dark matter, forming a tidal stream that wraps around the Milky Way. These stellar streams are like galactic breadcrumbs, tracing the path of the Sagittarius dwarf's demise and providing direct observational evidence of galactic mergers. The absorption of the Sagittarius dwarf has likely contributed stars to the Milky Way's halo, and potentially even influenced the flaring of our galactic disk and the formation of its spiral arms, demonstrating how these smaller interactions contribute to the growth and evolution of larger galaxies.
45. Magellanic Clouds Interaction. The Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, are two prominent irregular dwarf galaxies, the largest satellites of the Milky Way, and they are engaged in a complex gravitational dance that profoundly influences our galaxy. These two clouds are visible to the naked eye from the southern hemisphere and are gravitationally bound to the Milky Way, orbiting our galaxy. Their mutual gravitational interaction and their approach towards the Milky Way are causing significant tidal forces. The LMC, in particular, is a substantial dwarf, and its gravitational pull is thought to be responsible for warping the Milky Way's disk, creating its observed stellar warp. Recent observations suggest the LMC is on its first close approach to the Milky Way and is destined to merge with our galaxy in about 2.4 billion years, an event that will likely trigger a burst of star formation in the Milky Way's central regions and potentially even perturb the supermassive black hole Sagittarius A star. These interactions highlight the dynamic nature of galactic neighborhoods and the ongoing assembly of galaxies. 46. Galactic Cannibalism. Galactic cannibalism is a pervasive and fundamental process in the universe, where larger galaxies grow by gravitationally attracting, disrupting, and absorbing smaller satellite galaxies. The Milky Way is an active participant in this cosmic feast, having assimilated numerous smaller galaxies throughout its history, and continuing to do so today. The Sagittarius dwarf spheroidal galaxy is a prime ongoing example, currently being torn apart by our galaxy's tidal forces, leaving behind streams of stars. Evidence of past cannibalism is seen in the Milky Way's stellar halo, which contains ancient metal-poor stars and globular clusters that are thought to be remnants of these devoured galaxies. These mergers contribute to the growth of the larger galaxy, adding stars, gas, and dark matter, and can also trigger bursts of star formation, warp galactic disks, and influence the overall structure and evolution of the dominant galaxy. This process illustrates that galaxies are not static entities, but are constantly evolving through gravitational interactions and mergers over billions of years. 47. Tidal streams. Tidal streams are compelling observational evidence of ongoing or past galactic cannibalism in the Milky Way. These are long, narrow ribbons of stars and sometimes dark matter that have been stripped away from smaller satellite galaxies or globular clusters as they are gravitationally perturbed and torn apart by the immense tidal forces of a larger galaxy, like our own. As a dwarf galaxy orbits the Milky Way, its stars are pulled away by differential gravity, forming these characteristic streams that stretch across vast regions of the galactic halo, sometimes wrapping around the galaxy multiple times. The Sagittarius dwarf spheroidal galaxy provides the most prominent example, with its stellar streams spanning a significant portion of the sky. Studying these tidal streams allows astronomers to reconstruct the merger history of the Milky Way, identify its past galactic meals, and map the distribution of dark matter in the galaxy's outer halo, providing crucial insights into galaxy formation and evolution. 48. The stellar warp of the Milky Way. The Milky Way's galactic disk, far from being a perfectly flat plane, exhibits a noticeable and intriguing stellar warp. Imagine the outer edges of the disk gently bending upwards on one side and downwards on the opposite side, resembling a subtle S-shape or a warped vinyl record. This warp is not a static feature, but a dynamic one, affecting the distribution and motion of stars and gas in the outer regions of the disk. The exact cause of the Milky Way's warp is still debated, but the leading theory attributes it to the gravitational influence of our satellite galaxies, particularly the Large Magellanic Cloud. As the LMC orbits and passes close to the Milky Way, its immense gravity perturbs the outer disk, causing it to ripple and warp. This phenomenon provides direct evidence of the ongoing gravitational interactions between our galaxy and its companions, illustrating how even relatively small companions can exert significant influence on the grand structure of a spiral galaxy over cosmic timescales. 49. Flaring of the galactic disk. In addition to the stellar warp, another intriguing structural feature of the Milky Way's disk is its flaring. While the inner regions of the galactic disk maintain a relatively constant thickness, its outer edges are observed to thicken outwards, much like the bell of a trumpet. This means that the vertical extent of the stellar and gaseous disk increases significantly at larger distances from the galactic center. This flaring is observed in both the stellar disk and the distribution of hydrogen gas. The precise mechanism behind this flaring is still under investigation, but it is thought to be related to the dynamics of the galactic disk and its interaction with the surrounding dark matter halo. It could also be influenced by past or ongoing mergers with smaller galaxies, which deposit stars and gas into the outer disk, or by the cumulative effect of spiral density waves and stellar migration. The flaring provides important clues about the mass distribution of the galaxy, particularly in its outer regions, and the long-term evolution of the disk.
50. Galactic bar structure. At the very heart of the Milky Way, extending through its central bulge, lies a prominent and elongated structure known as the galactic bar. This bar is a dense, approximately 27,000 light-years long, rectangular-shaped collection of stars that rotates as a solid unit. It's not a static feature. Stars within the bar are constantly moving through it, but the overall structure persists. The galactic bar plays a crucial role in the dynamics and evolution of the Milky Way. It acts like a cosmic funnel, channeling gas and dust from the outer disk inwards towards the galactic center, fueling star formation in the central regions and potentially feeding the supermassive black hole Sagittarius A*. The bar's gravitational influence also helps to maintain and regulate the galaxy's spiral arm structure. Its discovery and detailed mapping, primarily through infrared observations that can penetrate obscuring dust, have significantly reshaped our understanding of the Milky Way's central architecture and its overall evolution as a barred spiral galaxy. 51. Bulge of the Milky Way. The bulge is a dense, roughly spherical or peanut-shaped structure located at the very center of the Milky Way, encompassing the galactic bar. It is a region of incredibly high stellar density, far more crowded than our solar neighborhood, with stars often only light weeks apart. The bulge primarily consists of older, metal-rich stars, indicative of early and rapid star formation, but also contains a significant population of younger stars and active star-forming regions, particularly within the central molecular zone. The dynamics of the bulge are complex, with stars exhibiting more random, less organized orbits compared to the disk. It is home to the supermassive black hole Sagittarius A*, and is a region of intense activity across the electromagnetic spectrum, emitting strong radio waves, X-rays, and gamma rays. The bulge represents a crucial component of the galaxy's structure, providing the gravitational backbone for the inner regions and offering insights into the galaxy's formation and early evolution. 52. Box/peanut-shaped bulge. Recent detailed observations, particularly from missions like Gaia, have revealed that the Milky Way's central bulge is not a simple sphere or ellipsoid, but rather possesses a distinctive and complex box or peanut shape when viewed edge-on. This peculiar morphology is a common feature in barred spiral galaxies and is thought to arise from the dynamics of the galactic bar. As the bar rotates, stars moving within it can be trapped in specific orbits that cause them to oscillate vertically, creating this characteristic three-dimensional structure. Effectively, the bar buckles vertically, forming the peanut shape. This boxy bulge is a direct consequence of the bar's gravitational influence and its evolution, providing strong evidence for the existence and stability of the Milky Way's central bar. Understanding the formation and dynamics of this box/peanut bulge is crucial for unraveling the complex processes that shape the central regions of our galaxy and how they interact with the broader galactic disk. 53. Central Molecular Zone. The Central Molecular Zone is a remarkable and extreme region of the Milky Way, located within the innermost few hundred light-years of the galactic center. It is characterized by an extraordinarily high concentration of dense molecular gas clouds, far exceeding the density of molecular gas found elsewhere in the galactic disk. These clouds are incredibly turbulent and warm, and they contain enough material to form millions of stars. Despite the abundance of raw material, star formation within the CMZ appears to be less efficient than expected, possibly due to the intense gravitational forces, magnetic fields, and high shear experienced in this extreme environment. However, when star formation does occur, it can be vigorous, leading to the formation of massive stars and clusters. The CMZ is also permeated by strong magnetic fields and is a source of powerful radio and gamma ray emissions. Studying this unique region provides crucial insights into the physical conditions and processes governing star formation and gas dynamics in the extreme environment of a galactic nucleus. 54. Gamma ray bubbles. Fermi bubbles. In a stunning discovery in 2010, astronomers using the Fermi Gamma Ray Space Telescope detected two colossal glowing structures extending symmetrically above and below the galactic center, known as the Fermi bubbles or gamma ray bubbles. These enormous lobes, each spanning approximately 25,000 light-years vertically, emit high-energy gamma rays and are thought to be the result of a powerful past outburst from the supermassive black hole Sagittarius A*, or an intense burst of star formation activity in the galactic center. The bubbles are filled with hot gas and cosmic rays, and their edges appear remarkably sharp, indicating a strong shock wave propagating through the galactic halo. These bubbles represent a powerful feedback mechanism, expelling energy and matter from the central regions of the galaxy into the halo, potentially influencing the flow of gas and the distribution of dark matter. Their existence provides direct evidence of energetic processes occurring in the galactic core, revealing a more active and dynamic past for the Milky Way's heart.
55. X-shaped bulge evidence. Further refining our understanding of the Milky Way's central structure, evidence has emerged suggesting that the box/peanut-shaped bulge might also possess an X-shaped morphology when viewed from certain angles. This X-shape is not a separate structure, but rather a more detailed description of the three-dimensional distribution of stars within the bar and bulge. It arises from the specific orbits of stars within the bar, which, as they oscillate vertically, can create an apparent X pattern when seen edge-on. This X-shape is a natural consequence of the gravitational dynamics of a highly evolved galactic bar. Astronomical observations, particularly using infrared telescopes that can peer through the obscuring dust in the galactic plane, have detected this X pattern in the distribution of red clump stars, a type of stellar standard candle, in the inner Milky Way. This discovery provides even stronger confirmation of the existence and complex dynamics of our galaxy's central bar, offering a detailed glimpse into the three-dimensional architecture of the galactic core. 56. Metallicities across the galaxy. The metallicity of stars and gas, referring to the abundance of elements heavier than hydrogen and helium, varies significantly across the Milky Way, providing a chemical fingerprint of its evolutionary history. Generally, there's a gradient. The innermost regions of the galactic disk and the central bulge tend to have higher metallicities, indicating that these regions have undergone more cycles of star formation and subsequent enrichment by supernovae and stellar winds. As one moves outwards into the disk, metallicities tend to decrease. The ancient stellar halo and globular clusters, which formed very early in the galaxy's history, are characterized by extremely low metallicities, as they formed from nearly pristine gas. This metallicity gradient is a powerful tool for tracing the formation timeline of the galaxy, showing how it gradually built up its heavier elements over billions of years. Stars with higher metallicities are more likely to host rocky planets, making this distribution relevant to the potential for life in different galactic neighborhoods. 57. Spiral density waves theory. The spiral density waves theory is the leading explanation for the persistence and appearance of the Milky Way's majestic spiral arms. Instead of the arms being fixed structures of stars that would quickly wind up due to differential rotation, this theory proposes that they are quasi-stationary patterns of enhanced density, much like a traffic jam on a highway. Stars, gas, and dust move into and out of these density waves. As interstellar gas and dust enter a density wave, they are compressed, triggering the collapse of molecular clouds and igniting new bursts of star formation. This explains why spiral arms appear brighter and bluer. They are continually populated by young, hot, luminous stars that are born within the wave. The older, redder stars simply pass through the wave and continue their orbits. These density waves are thought to be sustained by gravitational instabilities within the galactic disk and interactions with the galactic bar, providing a dynamic mechanism for the enduring beauty of our galaxy's spiral structure. 58. Role of supermassive black hole in shaping galaxy. The supermassive black hole at the Milky Way's center, Sagittarius A star, while relatively quiescent today, plays a profound and multifaceted role in shaping the galaxy over cosmic timescales. Its immense gravity acts as the anchor for the entire galaxy, influencing the orbits of billions of stars and the overall dynamics of the central regions. While it doesn't vacuum up stars indiscriminately, its gravitational potential well is a key factor in the stability and rotation of the galaxy.
In more active phases, common in the early universe, supermassive black holes can launch powerful jets and winds that expel vast amounts of energy and matter into the galactic halo, influencing star formation rates, heating the interstellar medium, and potentially regulating the growth of the galaxy itself, a process known as feedback. The Fermi bubbles are direct evidence of such past activity. Thus, Sagittarius A star is not merely a passive gravitational anchor, but an active participant in the grand evolutionary narrative of the Milky Way. 59. Radio emissions from the galactic center. The galactic center is a prolific source of radio emissions, making it one of the brightest radio sources in the sky. These radio waves provide an invaluable window into this highly obscured region, as they can penetrate the dense clouds of gas and dust that block visible light. The emissions originate from various phenomena: synchrotron radiation from high-energy electrons spiraling in magnetic fields, thermal emission from hot ionized gas, HII regions, and molecular line emission from dense molecular clouds. The most prominent radio source is Sagittarius A star, the location of the supermassive black hole, which exhibits strong, compact radio emission. Other notable features include vast filaments of magnetized gas, supernova remnants, and the central molecular zone, all glowing brightly in radio wavelengths. Radio astronomy has been crucial in mapping the structure and dynamics of the galactic center, revealing its complex magnetic fields, the distribution of gas, and the activity of Sagittarius A, offering insights otherwise impossible to obtain.
55. X-shaped bulge evidence. Further refining our understanding of the Milky Way's central structure, evidence has emerged suggesting that the box/peanut-shaped bulge might also possess an X-shaped morphology when viewed from certain angles. This X-shape is not a separate structure, but rather a more detailed description of the three-dimensional distribution of stars within the bar and bulge. It arises from the specific orbits of stars within the bar, which, as they oscillate vertically, can create an apparent X pattern when seen edge-on. This X-shape is a natural consequence of the gravitational dynamics of a highly evolved galactic bar. Astronomical observations, particularly using infrared telescopes that can peer through the obscuring dust in the galactic plane, have detected this X pattern in the distribution of red clump stars, a type of stellar standard candle, in the inner Milky Way. This discovery provides even stronger confirmation of the existence and complex dynamics of our galaxy's central bar, offering a detailed glimpse into the three-dimensional architecture of the galactic core. 56. Metallicities across the galaxy. The metallicity of stars and gas, referring to the abundance of elements heavier than hydrogen and helium, varies significantly across the Milky Way, providing a chemical fingerprint of its evolutionary history. Generally, there's a gradient. The innermost regions of the galactic disk and the central bulge tend to have higher metallicities, indicating that these regions have undergone more cycles of star formation and subsequent enrichment by supernovae and stellar winds. As one moves outwards into the disk, metallicities tend to decrease. The ancient stellar halo and globular clusters, which formed very early in the galaxy's history, are characterized by extremely low metallicities, as they formed from nearly pristine gas. This metallicity gradient is a powerful tool for tracing the formation timeline of the galaxy, showing how it gradually built up its heavier elements over billions of years. Stars with higher metallicities are more likely to host rocky planets, making this distribution relevant to the potential for life in different galactic neighborhoods. 57. Spiral density waves theory. The spiral density waves theory is the leading explanation for the persistence and appearance of the Milky Way's majestic spiral arms. Instead of the arms being fixed structures of stars that would quickly wind up due to differential rotation, this theory proposes that they are quasi-stationary patterns of enhanced density, much like a traffic jam on a highway. Stars, gas, and dust move into and out of these density waves. As interstellar gas and dust enter a density wave, they are compressed, triggering the collapse of molecular clouds and igniting new bursts of star formation. This explains why spiral arms appear brighter and bluer. They are continually populated by young, hot, luminous stars that are born within the wave. The older, redder stars simply pass through the wave and continue their orbits. These density waves are thought to be sustained by gravitational instabilities within the galactic disk and interactions with the galactic bar, providing a dynamic mechanism for the enduring beauty of our galaxy's spiral structure. 59. Role of supermassive black hole in shaping galaxy. The supermassive black hole at the Milky Way center, Sagittarius A star, while relatively quiescent today, plays a profound and multifaceted role in shaping the galaxy over cosmic timescales. Its immense gravity acts as the anchor for the entire galaxy, influencing the orbits of billions of stars and the overall dynamics of the central regions. While it doesn't vacuum up stars indiscriminately, its gravitational potential well is a key factor in the stability and rotation of the galaxy. In more active phases, common in the early universe, supermassive black holes can launch powerful jets and winds that expel vast amounts of energy and matter into the galactic halo, influencing star formation rates, heating the interstellar medium, and potentially regulating the growth of the galaxy itself, a process known as feedback. The Fermi bubbles are direct evidence of such past activity. Thus, Sagittarius A star is not merely a passive gravitational anchor, but an active participant in the grand evolutionary narrative of the Milky Way. 59. Radio emissions from the galactic center. The galactic center is a prolific source of radio emissions, making it one of the brightest radio sources in the sky. These radio waves provide an invaluable window into this highly obscured region as they can penetrate the dense clouds of gas and dust that block visible light. The emissions originate from various phenomena: synchrotron radiation from high-energy electrons spiraling in magnetic fields, thermal emission from hot ionized gas, HII regions, and molecular line emission from dense molecular clouds. The most prominent radio source is Sagittarius A star, the location of the supermassive black hole, which exhibits strong, compact radio emission. Other notable features include vast filaments of magnetized gas, supernova remnants, and the central molecular zone, all glowing brightly in radio wavelengths. Radio astronomy has been crucial in mapping the structure and dynamics of the galactic center, revealing its complex magnetic fields, the distribution of gas, and the activity of Sagittarius A star, offering insights otherwise impossible to obtain.
66. Evidence for dark matter from Milky Way. The Milky Way provides multiple lines of compelling evidence for the existence of dark matter, an enigmatic substance that constitutes the vast majority of our galaxy's mass. The primary evidence comes from the galaxy's rotation curve, which shows that stars and gas in the outer disk orbit too fast to be held by the visible matter alone, necessitating an additional, invisible gravitational component. Beyond the rotation curve, observations of the motion of satellite galaxies and globular clusters in the Milky Way's halo also indicate that they are moving under the influence of a much larger, more massive gravitational potential than visible matter can account for, pointing to an extensive dark matter halo. Furthermore, the dynamics of the stellar warp and flaring of the disk are also thought to be influenced by the dark matter distribution. All these observations consistently converge on the conclusion that the Milky Way is embedded within a vast, invisible halo of dark matter, without which its observed structure and dynamics would simply not make sense. 67. Streams from past mergers, like Gaia and Enceladus. The Milky Way's history is punctuated by numerous mergers with smaller galaxies, and the evidence of these ancient encounters is preserved in the form of stellar streams. One of the most significant discoveries in this regard is the Gaia and Enceladus, also known as the Gaia Sausage Stream, revealed by the Gaia mission. This massive stellar stream is composed of hundreds of thousands of stars that exhibit highly eccentric orbits, plunging deep into the Milky Way's inner halo and disk. Astronomers believe these stars were once part of a dwarf galaxy roughly the size of the Large Magellanic Cloud that merged with the Milky Way approximately 8 to 10 billion years ago. This collision was a major event in our galaxy's early history, contributing a significant fraction of the stars to the Milky Way's interstellar halo and thick disk. The discovery of Gaia Enceladus and other similar streams provides a direct archaeological record of our galaxy's assembly, illustrating how it grew through a process of accretion and mergers over billions of years. 68. Age of the Milky Way. Determining the precise age of the Milky Way is a complex task, as it involves understanding the formation of its various components, but astronomers have pieced together a compelling timeline. The oldest stars in our galaxy, found predominantly in globular clusters and the stellar halo, are estimated to be around 13.5 billion years old. This places the initial formation of the Milky Way's earliest structures very close to the age of the universe, which is about 13.8 billion years. The galactic disk and bulge formed somewhat later, with the thin disk continuing to form stars to this day. Our Sun, a relatively young star, is about 4.6 billion years old. The wide range of stellar ages reflects the galaxy's prolonged and continuous process of star formation, mergers, and evolution. The age of the oldest stars provides a robust lower limit for the age of the Milky Way, indicating that our galaxy is a truly ancient structure, a relic from the early cosmos. 69. Earliest stars in the galaxy. The earliest stars in the Milky Way, often referred to as population 2 stars, are the ancient relics that formed from nearly pristine gas shortly after the Big Bang. These stars are characterized by their extremely low metallicity, meaning they contain very few elements heavier than hydrogen and helium, as these elements had not yet been widely produced by previous generations of stars. They are primarily found in the galactic halo and within globular clusters, which are some of the oldest structures in the galaxy. The very first stars, theoretical population 3 stars, would have been completely metal-free and extremely massive, short-lived, and bright, but none have been directly observed. The population 2 stars we do observe are the direct descendants, or perhaps even some of the original longer-lived low-mass stars that formed during the Milky Way's infancy. Studying these ancient stars provides crucial insights into the chemical composition of the early universe and the initial conditions under which our galaxy began to assemble. 70. Chemical evolution over billions of years. The Milky Way has undergone a profound chemical evolution over its billions of years, a process that continuously enriches the galaxy with heavier elements. Initially, the universe was composed almost entirely of hydrogen and helium. The first stars, massive and short-lived, fused these light elements into heavier ones in their cores. When these stars died in supernova explosions, they dispersed these newly forged metals, elements heavier than helium, into the interstellar medium. Subsequent generations of stars then formed from this increasingly enriched gas, further contributing to the chemical inventory through their own life cycles and deaths. This process has led to a distinct metallicity gradient across the galaxy, with the oldest stars in the halo being metal-poor and the youngest stars in the disk being metal-rich. This ongoing chemical enrichment is fundamental to the formation of rocky planets and the emergence of life, demonstrating how the galaxy has transformed from a pristine, simple composition to the chemically complex environment we observe today.
71. Formation timeline of the galaxy. The formation of the Milky Way is a complex and protracted process spanning billions of years, beginning shortly after the Big Bang. The prevailing model suggests that it started as a massive cloud of gas and dark matter that began to collapse under its own gravity around 13.5 billion years ago. The oldest stars and globular clusters formed first, populating the nascent halo. Over the next few billion years, this collapsing cloud flattened into a rotating disk, and the central bulge began to form, possibly aided by early mergers. Evidence suggests a major merger event, like the one that formed the Gaia-Enceladus stream, occurred about 8 to 10 billion years ago, contributing significantly to the inner halo and thick disk. The galactic bar likely formed later, around 8 billion years ago, and the spiral arms emerged as dynamic features within the disk. Star formation has continued in the disk throughout its history, constantly replenishing its stellar population. The Milky Way is still evolving, growing through the accretion of smaller galaxies and the ongoing cycle of star birth and death, a testament to its dynamic and ancient origins. 72. Star migration inside the disk. Stars in the Milky Way's disk are not necessarily fixed to the spiral arm in which they were born. Instead, many undergo significant radial migration, moving inwards or outwards across the galactic disk over billions of years. This process, known as radial mixing or churning, is driven by gravitational interactions with the galaxy's spiral arms and the galactic bar. As stars pass through spiral density waves, they can gain or lose angular momentum, causing their orbits to shift to different radii. This means that a star might have formed in the inner disk but eventually migrated to the outer disk, or vice versa, without significantly changing the eccentricity of its orbit. Star migration has profound implications for understanding the chemical evolution of the disk, as it helps explain the observed distribution of metallicities and stellar populations. It also complicates efforts to reconstruct the precise birth locations of stars, including our Sun, adding a dynamic layer to our understanding of stellar kinematics within the galaxy. 73. Radial mixing of stars. Radial mixing, or churning, is a crucial process in the Milky Way's disk that describes the movement of stars inwards and outwards from their birth locations over cosmic timescales. Unlike simple orbital motion, which keeps stars generally at the same distance from the galactic center, radial mixing causes stars to change their average orbital radius. This phenomenon is primarily driven by gravitational interactions with transient spiral arms and the galactic bar. As stars encounter these density enhancements, they can be scattered to new orbits, effectively mixing populations of stars that were born at different radii. This mixing process is thought to be significant in shaping the observed chemical properties of the galactic disk, blurring the initial metallicity gradients and distributing stars with different chemical compositions across a wider range of galactic radii. Radial mixing helps explain why stars with very different ages and metallicities can be found in the same solar neighborhood, highlighting the dynamic and evolutionary nature of the Milky Way's stellar disk. 74. Structure of the galactic disk. The galactic disk is the most prominent and visually striking component of the Milky Way, a vast, flattened structure where most of the galaxy's stars, gas, and dust reside. It is characterized by its spiral arm pattern and its relatively thin profile compared to its diameter. However, the disk is not a monolithic entity. It has a complex multi-component structure. It consists of a thin disk, which is a younger, dynamically cooler population of stars, gas, and dust, about 1,000 light-years thick, where active star formation predominantly occurs. Surrounding and permeating this is a thick disk, an older, more diffuse, and dynamically hotter population of stars, extending up to 3,000 to 5,000 light-years vertically. Both disks are embedded within the larger dark matter halo. The disk structure is also marked by a central galactic bar, spiral arms, and features like warping and flaring at its edges. This intricate structure is a result of billions of years of gravitational collapse, rotation, star formation, and interactions with other galaxies. 75. Thin disk versus thick disk. The Milky Way's galactic disk is not a uniform slab, but is comprised of two distinct superimposed components, the thin disk and the thick disk, each with different properties that reflect their formation histories. The thin disk is the younger, more dynamically cool, meaning stars have more circular, orderly orbits, component, approximately 1,000 light-years thick. It contains the majority of the galaxy's gas, dust, and young metal-rich population 1 stars, including our Sun, and is where active star formation primarily takes place, especially in the spiral arms. In contrast, the thick disk is an older, more dynamically hot, meaning stars have more eccentric and vertically extended orbits, component, roughly 3,000 to 5,000 light-years thick. It is primarily composed of older, generally more metal-poor population 2 stars, and contains very little gas or dust. The thick disk is thought to have formed earlier and possibly through more turbulent processes, such as early mergers with dwarf galaxies, or through heating of the thin disk by such events. Distinguishing between these 2 disks is crucial for understanding the Milky Way's formation and evolution.
76. Stellar density gradient. The distribution of stars within the Milky Way is far from uniform. Instead, it exhibits a distinct stellar density gradient, particularly within the galactic disk and bulge. Stellar density is highest in the galactic center, where stars are packed incredibly tightly, sometimes only light weeks apart. As one moves outwards from the center along the galactic disk, the density of stars gradually decreases, becoming sparser in the outer regions. This gradient is not perfectly smooth, as it is punctuated by the higher densities within the spiral arms and the central bar. Similarly, vertically, stellar density is highest in the galactic plane and rapidly decreases as one moves above or below the disk into the halo. This gradient reflects the gravitational potential of the galaxy, with stars congregating in the deepest parts of the potential well. Mapping this density gradient is crucial for understanding the overall mass distribution of the Milky Way, including the influence of dark matter, and for modeling the galaxy's structure and dynamics. 77. Interstellar dust lanes. Interstellar dust lanes are striking features observed throughout the Milky Way, particularly in the galactic plane and towards the galactic center. These are not empty spaces, but rather regions of relatively dense interstellar dust, composed of tiny silicate and carbonaceous grains, which absorb and scatter visible light from background stars. As a result, they appear as dark, obscuring streaks or patches against the luminous backdrop of the galaxy, often delineating the spiral arms or obscuring the view of the galactic center. These dust lanes are intimately associated with molecular clouds, the birthplaces of stars, as dust grains play a crucial role in the cooling of gas and the formation of molecules, facilitating gravitational collapse. While they hinder observations in visible light, these dust lanes are vital components of the interstellar medium, containing the raw materials for future star and planet formation, and they become luminous when observed in infrared wavelengths. 78. Reddening of starlight. The reddening of starlight is a pervasive phenomenon observed throughout the Milky Way, caused by the scattering and absorption of starlight by interstellar dust particles. When starlight passes through dusty regions of space, shorter, bluer wavelengths of light are scattered more efficiently than longer, redder wavelengths. This preferential scattering means that the light that eventually reaches our telescopes has a relatively higher proportion of red light, making the star appear redder than it intrinsically is. This is the same principle that makes sunsets appear red on Earth. Reddening is distinct from the Doppler effect, redshift, which is caused by motion. By measuring the amount of reddening, astronomers can estimate the amount of dust between us and a distant star, providing crucial information about the distribution of interstellar dust in the Milky Way. This effect must be carefully accounted for when determining the intrinsic colors and temperatures of stars and when measuring cosmic distances. 70. Why we can't see the whole Milky Way from inside. From our vantage point within the Milky Way, it's impossible to see the entire galaxy in its grand, sweeping spiral form. This limitation arises from several factors. Firstly, we are embedded within the galactic disk itself, about 2/3 of the way out from the center, in the Orion arm. This is akin to trying to see the entire forest while standing amongst the trees. Our perspective is limited. Secondly, and most significantly, the vast amounts of interstellar dust and gas concentrated in the galactic plane heavily obscure our view, especially towards the galactic center and across the disk. This dust absorbs and scatters visible light, creating zones of avoidance where distant stars are completely hidden or severely reddened. While infrared and radio telescopes can pierce through much of this dust, they still provide only partial views. Therefore, our understanding of the Milky Way's overall shape and structure is painstakingly pieced together from observing other galaxies, mapping stellar distances and motions, and utilizing different wavelengths of light. 80. Night sky view of the Milky Way band. For anyone fortunate enough to be under a truly dark sky, far from urban light pollution, the Milky Way reveals itself as a magnificent, luminous band stretching across the celestial sphere. This ethereal glow is not a single distinct object, but rather the collective light from billions of stars, too numerous and distant to be resolved individually, all concentrated in the plane of our galactic disk. When we look towards this band, we are essentially looking along the edge of our flattened spiral galaxy, through the highest density of stars. The Milky Way band appears brightest and densest towards the constellation Sagittarius, which is the direction of the galactic center. Dark patches and streaks within this luminous band are not empty spaces, but rather interstellar dust lanes that absorb the light from background stars, creating silhouettes. This breathtaking view provides a visceral connection to our cosmic home, a reminder of the immense scale and beauty of the galaxy we inhabit.
81. Radio telescopes revealing hidden structure. Radio telescopes have been absolutely indispensable in revealing the hidden structure of the Milky Way, particularly those parts obscured by the vast amounts of interstellar dust that block visible light. Radio waves, with their much longer wavelengths, can penetrate these dusty veils, allowing astronomers to map the distribution of gas and the dynamics of the galaxy's most obscured regions. Observations of 21-centimeter radiation from neutral hydrogen gas have been crucial for tracing the spiral arm structure, measuring the galaxy's rotation curve, and identifying the warping and flaring of the disk. Radio observations also reveal the presence of molecular clouds, star-forming regions, supernova remnants, and the powerful emissions from the supermassive black hole, Sagittarius A star, at the galactic center. Without radio astronomy, our understanding of the Milky Way's overall structure, its gas dynamics, and the processes occurring in its core would be severely limited, making it a cornerstone of galactic research. 82. Impact of supernova feedback. Supernova feedback is a powerful and pervasive process that profoundly impacts the evolution of the Milky Way. When massive stars explode as supernova, they release enormous amounts of energy and matter into the interstellar medium. This feedback has several critical effects. Firstly, it violently ejects newly synthesized heavy elements into space, enriching the gas clouds from which future generations of stars and planets will form, driving the galaxy's chemical evolution. Secondly, the powerful shock waves from supernova compress surrounding gas, which can either trigger new star formation by creating dense pockets of gas, or, conversely, disrupt molecular clouds, halting star formation. Thirdly, supernova heat the interstellar medium to millions of degrees, creating vast bubbles of hot gas and driving galactic winds that can push gas out of the galactic disk into the halo. This energetic feedback regulates the star formation rate, sculpts the interstellar medium, and contributes to the overall dynamics and structure of the Milky Way. 83. Galactic winds. Galactic winds are powerful outflows of gas and cosmic rays driven from the disk of the Milky Way into its surrounding halo and beyond.
These winds are primarily powered by the collective energy input from intense star formation activity, particularly from massive stars that produce strong stellar winds and ultimately explode a supernova. The combined energy from these events can heat the interstellar medium to millions of degrees and push it outwards, creating vast plumes of gas that extend thousands of light years above and below the galactic plane. The Fermi bubbles are a dramatic example of such an outflow, possibly driven by past activity of the supermassive black hole. Galactic winds play a critical role in the chemical evolution of the galaxy by expelling enriched gas into the halo and potentially into the intergalactic medium, thereby regulating the star formation rate and preventing the galaxy from growing too large too quickly. They are a crucial component of the galaxy's ecosystem, connecting the disk to its halo and beyond. 84. Cosmic rays from the Milky Way. Cosmic rays are extremely high-energy particles, primarily atomic nuclei, mostly protons, and electrons, that travel through space at nearly the speed of light. The Milky Way is a source of cosmic rays, particularly those with lower energies, which are thought to be accelerated primarily by supernova remnants. The powerful shock waves from supernova explosions can accelerate charged particles to incredible velocities, creating a population of galactic cosmic rays that permeate the interstellar medium. These cosmic rays interact with interstellar gas and magnetic fields, producing secondary particles and electromagnetic radiation, including gamma rays. Higher energy cosmic rays, however, are believed to originate from extragalactic sources, such as active galactic nuclei or gamma-ray bursts. Studying cosmic rays provides insights into high-energy astrophysical processes, magnetic fields in the galaxy, and the composition of the interstellar medium, though their paths are bent by galactic magnetic fields, making it difficult to pinpoint their exact origins within the Milky Way. 86. How the galaxy produces magnetic fields. The Milky Way, like many spiral galaxies, is permeated by a complex and pervasive magnetic field. This galactic magnetic field is thought to be generated and maintained by a process called a galactic dynamo. This dynamo mechanism involves the large-scale differential rotation of the galactic disk, where inner parts rotate faster than outer parts, coupled with turbulent motions of ionized gas, plasma, within the interstellar medium, driven by processes like supernova explosions and stellar winds. These motions stretch and twist existing magnetic field lines, amplifying them and creating new ones, much like a dynamo generates electricity. The magnetic field lines are generally aligned with the spiral arms, but they also exhibit more complex structures, including a toroidal component in the disk and a poloidal component extending into the halo. These magnetic fields play a crucial role in the dynamics of the interstellar medium, influencing star formation, the propagation of cosmic rays, and the overall structure of the galaxy. 86. Interaction with intergalactic medium. The Milky Way is not an isolated entity, but is constantly interacting with the vast, diffuse intergalactic medium, the IGM, that fills the space between galaxies. This interaction is a two-way street. On the one hand, the Milky Way draws in fresh, relatively pristine gas from the IGM, which falls into the galactic halo and eventually fuels new star formation in the disk. This inflow of gas is crucial for sustaining the galaxy's star-forming activity over billions of years. On the other hand, galactic winds, driven by supernova and supermassive black hole activity, expel gas, heavy elements, and cosmic rays from the Milky Way into the IGM. This outflow enriches the surrounding intergalactic space with metals, forged within stars. These complex interactions are fundamental to the galaxy's baryonic cycle, regulating its growth, star-forming rate, and chemical evolution, and highlighting its dynamic relationship with its cosmic environment.
87. Escape velocity from the galaxy. The escape velocity from the Milky Way is the minimum speed an object needs to break free from the galaxy's gravitational pull and journey into intergalactic space. Unlike the escape velocity from a planet or star, which is relatively constant, the galactic escape velocity varies significantly depending on an object's location within the galaxy. It is highest near the galactic center and decreases with increasing distance. Near the Sun's position, the escape velocity is estimated to be around 500 to 550 kilometers per second. This speed is considerably higher than the Sun's orbital speed of 220 kilometers per second. Objects that reach or exceed this velocity, such as hypervelocity stars, are destined to become intergalactic wanderers. The escape velocity is a crucial parameter for understanding the total mass of the Milky Way, especially the contribution of its dark matter halo, as it directly relates to the galaxy's gravitational potential. 88. How many stars escape the galaxy? While the vast majority of stars remain gravitationally bound to the Milky Way for their entire lifetimes, a small but significant number of stars do manage to escape the galaxy's gravitational pull. These are known as hypervelocity stars, and their numbers are relatively small compared to the total stellar population. Estimates suggest there are likely thousands to tens of thousands of hypervelocity stars currently fleeing the Milky Way into intergalactic space. These stars are typically ejected at extreme speeds, hundreds of kilometers per second, due to violent gravitational slingshot events, most commonly from close encounters with the supermassive black hole Sagittarius A star at the galactic center, or less frequently from supernova explosions in binary systems. The stars that escape are usually single stars, as binary systems would likely be disrupted by the ejection mechanism. While not a major loss for the galaxy's overall stellar count, their existence provides unique insights into the extreme dynamics of the galactic core and the gravitational potential of the Milky Way. 89. How many stars escape the galaxy? The Milky Way is far from a static, finished product. It is a living, breathing, and still growing galaxy. Multiple lines of evidence confirm its ongoing growth and evolution. Firstly, it continues to accrete and assimilate smaller satellite galaxies, a process known as galactic cannibalism. The Sagittarius dwarf spheroidal galaxy is a prime ongoing example, with its stars being stripped away and added to the Milky Way's halo. The Gaia Enceladus stream reveals a more ancient, significant merger. Secondly, the Milky Way is continuously drawing in fresh, relatively pristine gas from the intergalactic medium, which falls into the galactic halo and then the disk, providing raw material for new star formation. This inflow helps replenish the gas consumed by stellar birth. Thirdly, active star formation is still rampant within the galactic disk, particularly in the spiral arms, constantly adding new stars to its population. Finally, the eventual merger with the Andromeda Galaxy in billions of years will represent a massive growth spurt, transforming our galaxy into an even larger elliptical one. 90. Why the Milky Way isn't a perfect spiral. Despite its iconic spiral classification, the Milky Way is far from a perfectly symmetrical or pristine spiral galaxy. Several factors contribute to its somewhat irregular and dynamic appearance. Firstly, the presence of a prominent galactic bar at its center distorts the inner spiral arms, causing them to emerge from the ends of the bar rather than the very core. Secondly, the differential rotation of the disk constantly winds up and reshapes the spiral arms, which are thought to be transient density waves rather than static structures. Thirdly, ongoing gravitational interactions with satellite galaxies, particularly the Large Magellanic Cloud, cause warping and flaring of the galactic disk, further deviating it from a flat, perfect plane. Past and ongoing mergers with smaller galaxies, like the Sagittarius dwarf, also introduce gravitational perturbations and deposit stars into the halo and disk, adding irregularities. These dynamic processes ensure that the Milky Way is a constantly evolving and somewhat imperfect, yet endlessly fascinating cosmic entity. 91. Satellite galaxies of the Milky Way. The Milky Way is surrounded by a retinue of smaller, gravitationally bound satellite galaxies, forming its own miniature galactic system. The two largest and most famous are the Large Magellanic Cloud and the Small Magellanic Cloud, both irregular dwarf galaxies visible to the naked eye from the southern hemisphere. Beyond these, there are dozens of other known dwarf galaxies, mostly dwarf spheroidal or dwarf irregular types, that orbit the Milky Way. Examples include the Sagittarius dwarf spheroidal, which is currently being absorbed, and the Fornax dwarf. These satellite galaxies are often very old and metal-poor, providing insights into the early universe. Their orbits are highly influenced by the Milky Way's dark matter halo, and their gravitational interactions can significantly impact our galaxy, causing warps in its disk and contributing to its growth through galactic cannibalism. The study of these companions provides a crucial context for understanding the Milky Way's formation and evolution.
92. Newly discovered faint dwarf galaxies. In recent years, astronomical surveys, particularly those enabled by the Gaia mission, have led to the discovery of numerous new, extremely faint dwarf galaxies orbiting the Milky Way. These newly found satellites are often incredibly diffuse and low in luminosity, making them exceptionally difficult to detect against the backdrop of our own galaxy. Many are ultra-faint dwarf galaxies, containing only a few thousand stars, making them the darkest and most dark matter-dominated galaxies known. These discoveries significantly increase the known number of Milky Way satellites, suggesting that the galaxy's halo is even richer in substructure than previously thought. Studying these faint dwarfs is crucial for understanding galaxy formation models, especially in the context of dark matter. They serve as direct probes of the smallest building blocks of galaxies and provide insights into the early universe, as many of these relics are thought to be primordial, relatively undisturbed by the cosmic evolution. 93. Gas inflow from the halo. The Milky Way is not a closed system. It continuously draws in fresh gas from its surrounding halo, a process vital for sustaining its long-term star formation. This gas inflow originates from the intergalactic medium and from gas that was previously expelled from the galaxy by galactic winds, now cooling and falling back. As this cooler, often metal-poor gas falls towards the galactic disk, it mixes with the existing interstellar medium, replenishing the raw material for new stars. This continuous accretion of gas from the halo is thought to be a crucial mechanism that allows the Milky Way to maintain its star formation rate over billions of years, despite constantly converting gas into stars. Without this ongoing inflow, the galaxy would eventually run out of fuel for star formation. Observations of high-velocity clouds of gas falling towards the disk provide direct evidence for this vital process, demonstrating the dynamic exchange of matter between the galactic disk and its halo. 94. Gas outflow from star formation. While gas inflow fuels star formation, the process of star formation itself also drives significant gas outflow from the Milky Way, creating a dynamic cycle. The most massive stars, born in prodigious star-forming regions, exert powerful feedback on their environment. Intense stellar winds from these young, hot stars and the subsequent supernova explosions at the end of their lives inject enormous amounts of energy into the interstellar medium. This energy heats the gas to millions of degrees and can drive it outwards, creating vast bubbles and powerful galactic winds that push gas out of the galactic disk into the halo and potentially even into the intergalactic medium. This gas outflow is crucial for regulating the galaxy's star formation rate, preventing it from converting all its gas into stars too quickly. It also enriches the halo and intergalactic medium with heavy elements forged within stars, demonstrating the complex interplay between stellar processes and galactic-scale gas dynamics. 95. Origin of elements inside the Milky Way. The elements that make up everything in the Milky Way, including ourselves, have a fascinating and violent cosmic origin story. The very lightest elements, hydrogen, helium, and a trace of lithium, were forged in the Big Bang itself. All other heavier elements, often referred to as metals by astronomers, were created much later through the processes of stellar nucleosynthesis within stars.
In the cores of stars like our Sun, hydrogen is fused into helium, and then helium into carbon and oxygen in more massive stars. Even heavier elements, up to iron, are formed in the cores of very massive stars. However, the creation of elements heavier than iron, such as gold, silver, and uranium, require even more extreme conditions, typically occurring during supernova explosions or the mergers of neutron stars. These elements are then dispersed into the interstellar medium by stellar winds and stellar deaths, enriching the galaxy and becoming the building blocks for subsequent generations of stars, planets, and life. The Milky Way is a giant recycling plant for the elements of the universe. 96. Distribution of black hole binaries. Black hole binaries, systems where a stellar mass black hole orbits a companion star, are distributed throughout the Milky Way, though their precise numbers and locations are difficult to pinpoint. These systems are typically detected when the black hole actively accretes matter from its companion, forming an accretion disk that heats up and emits powerful X-rays. Such X-ray binaries are observed across the galactic disk, particularly concentrated towards the galactic center and within the spiral arms, where stellar density and star formation rates are higher. However, the vast majority of stellar mass black holes are likely isolated or in quiescent binaries, making them extremely challenging to detect. Observations also suggest a population of black hole binaries within globular clusters, where the high stellar density can lead to dynamic interactions that form these systems. Understanding their distribution helps astronomers map the population of massive stellar remnants and study the dynamics of accretion onto black holes within our galaxy.
97. Star clusters near the galactic center. The region near the galactic center is home to an extraordinary concentration of star clusters, representing some of the densest and most massive stellar groupings in the Milky Way. These include both very young, massive open clusters and ancient, metal-rich globular clusters. The Arches cluster and the Quintuplet cluster are two of the most massive and youngest star clusters known in our galaxy, located just a few hundred light-years from Sagittarius A star. They contain hundreds of thousands of very luminous, massive stars, making them incredibly bright sources of infrared and X-ray radiation. Their presence indicates ongoing, vigorous star formation in the extreme environment of the central molecular zone. Additionally, a significant population of ancient globular clusters is found in the inner bulge, distinct from those in the halo. These clusters provide crucial insights into star formation under extreme conditions, the chemical evolution of the inner galaxy, and the dynamics of stellar populations in the immediate vicinity of the supermassive black hole. 98. Measuring distances across the galaxy. Measuring distances across the vastness of the Milky Way is one of the most fundamental and challenging tasks in astronomy, relying on a cosmic distance ladder of interconnected techniques. For nearby stars, the most accurate method is parallax, which measures the apparent shift in a star's position as Earth orbits the Sun. For greater distances within the galaxy, astronomers rely on standard candles, objects with known intrinsic luminosities. These include Cepheid variable stars, whose pulsation periods are directly related to their luminosity, and RR Lyrae stars. By comparing their known intrinsic brightness to their observed apparent brightness, their distance can be calculated. Other methods include using the spectral properties of stars, the expansion of supernova remnants, and the motions of star clusters. The Gaia mission has revolutionized distance measurements for billions of stars, providing an unprecedented 3D map of our galactic neighborhood and recalibrating the entire galactic distance scale, essential for understanding the Milky Way's structure and evolution. 99. Parallax limits inside the Milky Way. Parallax, the apparent shift in a star's position due to Earth's orbital motion around the Sun, is the most direct and precise method for measuring stellar distances. However, its effectiveness has significant limits within the vast expanse of the Milky Way. As stars become more distant, their parallax angle becomes infinitesimally small, making it incredibly challenging to measure accurately. Historically, ground-based telescopes could measure parallax for stars out to only a few hundred light-years.
Space missions like Hipparcos extended this to about 1,000 light-years. The revolutionary Gaia mission has pushed this limit dramatically, precisely measuring parallaxes for over 1 billion stars, out to many thousands of light-years, effectively mapping a significant portion of the galactic disk. Yet, even with Gaia, stars in the most distant parts of the Milky Way, across the entire disk, and certainly in the halo, remain beyond the reach of direct parallax measurements, highlighting the persistent challenge of mapping our galaxy's full extent. 100. Why mapping the Milky Way is so difficult. Mapping the Milky Way is an immensely difficult undertaking, akin to trying to draw a map of your hometown while standing in its busiest square, blindfolded, and only allowed to listen to the sounds. Our primary challenge is our unique internal perspective. We are embedded within the galaxy's disk, preventing us from getting an external bird's-eye view. This internal position means that vast amounts of interstellar dust and gas obscure our view, particularly towards the galactic center and across the disk, making it impossible to see the full extent of its spiral arms or its distant regions in visible light. Furthermore, the sheer scale of the galaxy, the immense distances involved, and the dynamic nature of its components, stars are constantly moving, gas is flowing, add layers of complexity. The presence of invisible dark matter, which dominates the galaxy's mass but cannot be directly observed, also complicates mass and structure determination. Despite these formidable obstacles, astronomers continually develop innovative techniques utilizing observations across the entire electromagnetic spectrum and missions like Gaia to painstakingly piece together an increasingly detailed and dynamic picture of our magnificent galactic home.